Okay, so today's deep dive is going to be a wild one. We got some listener questions about the universe, and I mean like the really big questions.
Oh, yeah. Like what?
Quarks, black holes,
Yeah.
even things like the fabric of reality. Crazy, right?
Sounds intense.
Oh, it is. And the best part, these aren't your typical physics class questions. This listener, they went deep. Get ready for some serious aha moments.
Mm-hmm.
So they're super curious about quarks. You know, those tiny particles that make up, well, everything.
Right, right.
And get this, they're calling them zygotes in a cosmic soup, which is, I mean, I've heard the cosmic soup analogy before, but zygotes, that's a new one.
Zygotes. Wow. Okay, so they're thinking about the very beginning, the formation of.
Exactly. Like the Higgs field, the thing that gives particles mass, might actually be shaping how those quarks interact and form, bigger structures.
Now, that's a fascinating thought.
Right. It's like they're saying the Higgs field isn't just some background hum.
Yeah.
But this active force shaping the universe at its core.
I see. I see. So they're suggesting it's not just about giving mass, but influencing the interactions, the relationships between particles.
Yes. And that idea of a force driving complexity, it makes me think about that concept. What is it? Emergence.
In complex systems, yeah.
Emergence. Okay, I
Yeah.
see where you're going with this. It's like, think about an ant colony.
Okay, an ant colony, right.
Each ant, on its own, follows simple rules, but put them all together, and you get this incredibly complex, organized society.
Wow. Never thought about it that way.
Right. Or take the human brain. Billions of neurons firing signals, somehow creating consciousness, thoughts, emotions, all from these basic interactions. It's mind-boggling when you really try to wrap your head around it.
Absolutely. And that's what our listener is getting at, this idea that maybe, just maybe, the Higgs field is doing something similar on a universal scale. Like it's the driving force behind those fundamental interactions that create everything we see.
So we've gone from quarks to ant colonies to the human brain, all thanks to this one question. But buckle up, because their next question takes us even deeper into the quantum realm.
Oh, let's hear it.
Spectral particles.
Now we're venturing into, shall we say, a very complex and theoretical area of physics.
Yeah, spectral particles is where I started to feel a little lost, to be honest. But that's why you're here. You can make even the most mind-bending physics concepts, make sense.
I'll do my best. So to understand what the listener's getting at with spectral particles, we need to go back to quarks for a moment.
Okay, back to quarks. Got it.
Specifically, there's this property they have called color charge.
Color charge. That rings a bell, vaguely, from high school physics. But are we talking like actual colors here? Are quarks running around like red, blue, and green?
That's a great question, and it shows how sometimes physics borrows everyday language for these really complex ideas. When we talk about color charge in quarks, it has nothing to do with actual visual colors. It's more of an analogy, a way to understand how these particles interact.
Okay, so not like the color of a shirt. Got it.
Exactly. You see, quarks have this incredible ability to interact through what we call the strong force.
Just strong force, right. That's the one that holds the nucleus of an atom together, right? Like super glue for the universe.
That's a good way to think about it. And it's through this color charge that they interact with that force. It's how they can bind together to form those protons and neutrons.
So it's like quarks have their own language, and this color charge is like the grammar, making sure the sentences make sense.
That's actually a fantastic way to put it. And what's fascinating is that our listener, they're drawing a parallel between this quark grammar, this color charge, and the theoretical properties of these spectral particles.
So they're looking for a hidden code, like a deeper connection between these ideas. They're quite the detective.
They are. And while the connection between color charge and spectral particles is very theoretical, it's that kind of outside-the-box thinking that leads to those big aha moments in science. Sometimes the wildest ideas lead to the biggest breakthroughs. It's true. Sometimes you got to think outside the box, break those boundaries to see what's really out there.
I love that. So it's like they're saying, what if these rules governing these tiny particles are a reflection of some bigger cosmic order? And speaking of big cosmic orders, their next question throws in a real brain twister from the world of math, the Riemann hypothesis.
Ah, yes. Our listener is suggesting a connection between this famous mathematical puzzle and the energy levels we see inside quantum systems. Fascinating stuff, but pretty speculative, of course.
Okay, so from quarks, we're jumping to what might be the biggest unsolved problem in mathematics. I got to admit, I haven't thought about the Riemann hypothesis since, well, ever. Could you maybe give us a little refresher?
Sure thing. So at its core, The Riemann hypothesis, it's all about prime numbers. Those numbers you can only divide by 1 in themselves.
Right, prime numbers, got it.
So this hypothesis, it proposes a way to predict where these prime numbers pop up along a specific mathematical line. It's a pretty complex idea that's been puzzling mathematicians for ages, well over a century now.
No kidding. I remember those prime numbers in school, and I never understood what all the fuss was about. And now we're saying this mathematical puzzle could be hiding secrets about the energy levels of quantum systems. That's a pretty big leap, isn't it?
It is a big leap, no doubt. And it really highlights how our listener, they're searching for these grand connections between things that seem, at least on the surface, totally unrelated.
I mean, the very idea that a math equation could unlock secrets about the universe at its most fundamental level makes you wonder what other connections are out there just waiting to be discovered,
Exactly. It's a big, mysterious universe out there.
And speaking of mysterious, our listener's last question throws us another curveball. Black holes. And not just any black holes, but black holes in a pixelated universe.
Right, so now we're diving headfirst into quantum gravity, questioning how our whole understanding of black holes might change if we think of space-time itself not as this smooth, continuous thing, but more like something built of tiny, indivisible pieces.
Okay, so instead of a smooth sheet like a trampoline, space-time is more like a trampoline made of, say, Legos.
Exactly. It's like imagining the fabric of space-time as this digital image made up of pixels. That's the concept some physicists are exploring, quantized space-time. They think it might be the key to finally bringing together quantum mechanics and general relativity, two of the most fundamental theories in physics, but theories that haven't quite gotten along so far.
Right, two big pieces of the puzzle.
Right.
So, hypothetically speaking, let's say the universe is pixelated, like that Lego trampoline. What does that mean for these black holes?
Well, if space-time has a smallest possible unit, a pixel, so to speak, then there's a limit to how small anything, even those intense gravitational wells created by black holes, can get.
So, like a minimum size limit for those gravity wells. Does that mean we need to rethink what we know about singularities? Those points of, like, infinite density at the heart of black holes?
That's the million-dollar question. If space-time is pixelated, singularities, as we currently imagine them, might not be possible, at least not as these infinitely small points.
Whoa. So, no more infinite weirdness at the center of black holes. What's in there then? If not a singularity, what takes its place?
That's the real head-scratcher. What happens to everything that falls into a black hole, all that matter and energy, if it can't collapse into a point? Does it just get squeezed down to the smallest possible size, like that space-time pixel, or does something totally different happen? These are questions at the forefront of research in quantum gravity.
It's like our listener just tugged on a loose thread, and suddenly our whole understanding of black holes starts to unravel. I gotta say, it's kind of exhilarating, but also a little terrifying, don't you think?
It's the best kind of science, the kind that keeps you up at night. But we haven't even touched on the listener's most intriguing question yet.
Oh, you're right. We still have to talk about DNA. DNA. Wait, so we're talking quarks, black holes, and now DNA. This deep dive is like a roller coaster through the universe.
Right. Our listener, they're really thinking big picture stuff, connecting all these different areas of science. And with DNA, they're suggesting it might be more than just a blueprint.
More than a blueprint. Okay, now you've got to explain that one.
So we usually think of DNA as this instruction manual for life, right? But what if it's also acting as a kind of antenna?
An antenna?
Yeah.
You mean like picking up signals? Signals from where?
Well, that's where things get really interesting. We're talking about the possibility of DNA interacting with, say, subtle energies, maybe even consciousness itself. It's definitely on the fringes of scientific thought.
So we're wading into, like, intuition, precognition, telepathy even.
That's the general idea, but I have to be honest, these ideas, they're not exactly mainstream science. There's a lot of skepticism out there.
Right. Not a lot of hard evidence yet.
Exactly. But there are researchers, serious researchers, who believe DNA might hold secrets that go way beyond what we currently understand. Secrets about physics, biology, maybe even consciousness itself.
Wow. It's a lot to take in. I mean, if space-time can be pixelated, if singularities might not even be a thing, who knows what mysteries DNA could be hiding?
Exactly, and I think that's what makes these deep dives so amazing. It's about asking those huge, mind-blowing questions, even if we don't have all the answers yet. It's about pushing those boundaries,
Absolutely. A huge thank you to our listener for these incredible questions. You've given us a lot to think about, that's for sure. And to everyone listening, remember, the universe is full of mysteries. Don't be afraid to ask those big questions. Keep exploring, Keep that curiosity alive, and who knows what incredible discoveries await. This is The Deep Dive, signing off. Until next time.